Justin Miller, Arts College Physics. Good day. So we are going to continue onward looking at some vectors. There's a couple properties about vectors in general that will allow us to start to consider adding vectors together, doing a little vector algebra. So let us start off with these couple properties first. And nope. Some vector properties. So the first property that we want to discuss here is that a vector can be translated anywhere in space and remain the same vector. Vector can be translated anywhere in space and remain the same vector. If we do not change its length or the direction it is pointing. If its length magnitude and direction remain unchanged. So what does this really mean? Well, we could take a coordinate system because it's easiest to look at something in a coordinate system. And we can just kind of say that, hey, we've got this coordinate system, we've got X, we've got Y, and we'll go ahead and throw in some vector here, right? So we'll say that we've got this vector right here. We'll call that vector A hat. Right now, I have it starting at the origin and going over. It has a certain length that's scaled to be its magnitude that points at some direction that is some angle relative to the positive X direction. That's great. I can take this vector and move it anywhere I want. And as long as I don't rotate it, change its direction, or change its length, change its magnitude, we have that it remains the same. So I can take this vector and I can move it over here and say, well, just as well, that's A hat as well. Or I could put it down here. That's A hat, or I could just move it over here and say that's A hat. But if I take this and I say, well, actually, I'm going to go something like this. This does not equal A hat. That's a completely different vector. I've changed its direction. Or if I take it and I just make it in the same direction but shorter, this does not equal A hat. Shorter, different direction. As long as I keep the same length, though, and the same direction that it's pointing, it's the same vector. So that's going to be useful for when we actually start adding things together and seeing how to really come to some conclusion about how we need to approach them algebraically. All right, so there's one property of a vector. Another property that we want to focus our attention on is, well, what does it mean to have a negative vector? A negative vector is just its positive counterpart pointing in the opposite direction. Both positive and negative of a given vector have the same magnitude. Just opposite directions. That's it. So, if we want to look at what's A hat versus negative A hat, well, we should just go like this. If I go ahead and say again, we've got some coordinate system. And I say, well, there's some A hat here. What does negative A hat look like? Well, negative A hat looks like this vector rotated by 180 degrees. Has the same exact magnitude, just points in the opposite direction. So this one would be, I wish I would have had that more on the origin. Well, looks about the same, right? Ooh. Straight as I want it. This would be negative A hat. What again is the difference between these two? The difference is there's a 180 degree angle in between them. Arrgh. That's it. Same magnitude, opposite directions. So again, with the ability to translate things, I could also say, hey, I don't just have to be right there. I could have that my A hat's over here. And I could say, well, negative A hat's over here. And as long as they have the same magnitude, length, and they point in opposite directions, we're good. So those two would specify A hat and negative A hat. We can also look at this in terms of unit vector notation. Unit vector notation we can write A hat is equal to some AX I hat plus AY J hat. Well, what happens if we want negative A hat? Well, negative A hat is equal to negative A sub X I hat minus A sub Y J hat. The negative sign really just distributes through into the individual components. So we get a negative A sub X I hat minus A sub Y J hat. So not saying that these are necessarily positive and these are necessarily negative, it's just opposite, right? The I hat and the negative I hat are in opposite directions. So negative J hat, positive J hat. Negative I hat, positive I hat. So if we look at that specifically on the coordinate system, it's easier to see a little bit. And let's just do that. So I'm going to draw this out. Again, we can take our good old vector A hat that we've been using. We got ourselves an A hat there. And what is this A hat? What is it composed of? That's right, it's got an I hat and J hat component, right? So this would be some A sub X I hat and some A sub Y J hat. What happens if we want to make negative A hat? Well, it has a negative A sub X I hat and a negative A sub Y J hat. So if we go ahead and take this and basically rotate this one by 180 degrees, the same length, that looks pretty good. This would be negative A sub X I hat, and then we take this one, flip it around, translate it over here, negative A sub Y J hat. Well, what do we have? The vector goes from here down to there, and that would be our negative A hat there. So in either case, whether we're looking just specifically at 180 degree rotation, or looking at it in terms of changing the X and Y components to be the opposite of what they originally were for its positive counterpart, you get the same result. That's it. Changing X and Y to be their opposite values, opposite directions, is ultimately 180 degree rotation in two-dimensional coordinate space. So those are a couple of nice things regarding individual vectors that we're going to utilize to take a look at something. Namely, this first part, but this will come in handy too. So let's just go ahead and look at some vector addition. So we want to take two vectors now, or more. We'll just start with two though, and say I want to find out what the resultant vector is, the vector sum of two individual vectors being added together. So, vector addition. Well, the easiest way to start to look at this first is graphically. So in terms of a graphical representation, when you add vectors together, you just place them tail to tip. Graphically, adding vectors together. Place the first vector. At some position. 0, 0 is a good place. Not necessary, but it is a good place. Start at the origin. And then place the tail of the vector you are adding to it at its tip. If you are adding more than one vector, proceed to place the next one's tail, the next vector's tail, at the tip of the last vector. The resultant vector begins at the tail of the first vector vector and ends at the tip of the last vector. All right, so lots of words there. That's great. Ultimately, we're going to use the fact that we can translate vectors around to any location to take successive vectors and place their tail at the tip of, well, the preceding vector. So let's just look at a nice little example regarding this. Not example, but illustration, if you will. This will endow us with the ability to extract out how we will mathematically, algebraically, if you will, deal with vector addition. All right, so let's say that we've got two vectors. Add the two vectors. Graphically. We're going to say that we've got an A hat and a B hat. A hat, we're just going to say, looks like this. It has a specific direction that it points, and it has a specific magnitude scaled to be its length. And then we've also got ourselves a b hat. I'm going to say b hat looks like this. Points in a different direction and, well, has a different magnitude. Let me make it a little shorter. There we go. Two different vectors. So we want to add these together graphically. A coordinate system, Cartesian coordinate system is usually pretty nice to go ahead and do this. So we can take ourselves a nice coordinate system here. We've got an X and a Y. Not too straight, but not too crooked. There we go. And what do we want to do? Well, we're going to take this first vector and we are going to translate it over such that its tail is at the origin. It's just a nice convenient spot. We could really put it anywhere, but it makes things a little bit easier to visualize. So let's just do that. Take this vector, I'm going to move it over here. So we've got something like this. There's an A hat. Boom, boom. All right, we've also got a B hat here, right? We want to add B hat to A hat. So we are going to take B hat and translate it such that its tail is at the tip of A hat. So I take it, I'm going to put it right here. So what do? Just do it. There's B hat, within reason. The vector that results, we could call C hat, if you will, or whatever really we want, A hat plus B hat, and starts at tail here of the first vector and ends at the tip of the last vector. So we've got this. That was messy. Let's just do this. That looks okay. All right, so it's supposed to be a straight line. Not using a ruler. That's okay. So we've got C hat here, where C hat is equal to A hat plus B hat. So that's how we form the resultant vector. So what we want to be able to do is appreciate how we get this mathematically. So let us do this. Let us think about the fact that both A hat and B hat can be represented in unit vector notation. So we can say that A hat is some A sub x I hat plus some A sub y j hat. That's great. And we can say that B hat is some B sub x I hat plus some B sub y j hat. There's our unit vector notation there. And what we want to note is, what is A hat plus B hat? How do we come to that conclusion? Well, let us look at this. So I can take this A hat here, and what I can do is I can resolve it into its individual components, right? So if I translate this down, and then this comes over, I've got some A sub x I hat there, and some A sub y j hat there. So there's the components there. Great. Well, I can do the same thing for B, right? B translates like this. Excuse me. Projection translates downward like that. And we've got that this is some B sub x I hat, and this is B sub y j hat. So there are those two individual vectors kind of broken down into their individual components, x component and y component. So what we want to know is, how do we get C hat? Well, let's note that any vector in 2 dimensions can be represented in unit vector notation. So we should be able to write that there is some C hat, which is some C sub x I hat plus some C sub y j hat. Well, that would get formed by going, let's see, this should be a little bit, by going down like this, going over like this. This would be C sub x I hat, this would be C sub y j hat, forming this big red outer triangle here. Well, now let's look at what C sub x and C sub y are really composed of, right? So if you look at this, C sub x is this total amount here. If I go over A sub x and then I go over b sub x, that's equal to c sub x, right? So we have that c sub x is equal to a sub x plus b sub x. That's it. Just take the components, x components of a and b, add them together, and we've got the x component of c. Likewise, if we want c sub y, well, that is some a sub y. We go up a sub y, and then we go up more b sub y. And there's our total c sub y. So we've got and c sub y is equal to a sub y plus b sub y. So, what do we have with this? Well, we've got ourselves that c hat is equivalent to a sub x plus b sub x I hat. Remember, this is c sub x right there, in the I hat direction, plus a sub y plus b sub y j hat. What does this tell us overall? Hey, if you want to form a resultant vector through vector addition of multiple vectors, you add all the x components of the individual vectors together in the I hat direction, add all the y components of the individual vectors in the j hat direction, and you've got yourself the resultant vector in unit vector notation. What happens if we want, well, the magnitude and direction? Well, again, we could note that this is c sub x, and this is c sub y right there. And if we wanted to expand on this a little bit, we could go ahead and say, what is the magnitude and direction of c hat? Spell that out here in a second. Magnitude and direction. It's then given by, well, we got ourselves the magnitude of c hat is going to be equal to the square root of the sum of the squares of its x and y components, which we've got the square root of c sub x squared plus c sub y squared, where c sub x and c sub y are ax plus bx and ay plus by respectively. So we've got this is then square root a sub x plus b sub x quantity squared plus a sub y plus b sub y quantity squared. There's our overall magnitude of the resultant vector. Square root of the sum of the squares of the x and y components. If we want the angle at which c hat is at, theta sub c, well, we've got that is gotten by looking at the arctangent of its y component divided by its x component, which is then equal to the arctangent of the quantity of ay plus dy divided by the quantity of ax plus bx. And that would be with respect to the positive x direction. So there we go. This is how we add vectors together. We have 5 vectors that we're adding together. We just keep on doing the same thing. And ultimately, add all the x components with x components, y components with y components, and formulate what the vector sum is. All right. So what we'll do is we'll put this to use, look at a nice little problem, and go from there. All right. Take care.